A bullet is fired from a gun, and the gun kicks back. A jet engine works like that. A stream of water is aimed at the heart of a fire, and the hose pushes back against the fireman. A jet engine works like that. And remember as a kid how you blew up balloons and let them sail across the room? A jet engine works like that. What do these seemingly unrelated things have to do with a jet engine? They're all related. They and the jet engine are all in the same family because each one reacts to an action of its own creation. Isaac Newton spelled it out for us. To every action, there is an equal and opposite reaction. The air rushing out of the balloon was the action. The balloon darting the other way was the reaction. When the water surged from the fire hose, that was the action. All the while, the hose pushed back in the opposite direction. That was the reaction. When the bullet sped out of the gun, that was the action. At the same moment, the gun kicked back. That was the reaction. A jet engine works on exactly the same principle. To every action, there is an equal and opposite reaction. A jet engine expels a continuous high-velocity stream of exhaust gases. That's the action. As a result, the engine thrusts forward. That's the reaction. And now you know why jet engines, and rocket engines too, are often called reaction engines. And you can see why the power of a jet engine is expressed in pounds of thrust rather than horsepower like your car engine. Now, how much thrust will a jet engine develop? Let's look at it this way. If we take the design engineer's thrust equation and put it in its simplest form, it boils down to this. Thrust equals mass times acceleration, or T equals M times A. Mass is a measure of the quantity of matter. In this case, the amount of air going through the engine. Acceleration is a change in velocity, or how much the air is speeded up as it passes through the engine. These two factors, then, are the main ingredients for thrust. The greater the mass of air flowing through the engine, the greater the thrust. The greater the acceleration of the air, the greater the thrust. Hang on to this T equals M times A concept. We'll find it's a handy tool to help us understand why engines are designed as they are. Now, before we look at real engines and real parts, let's spend just a few minutes building a very simplified engine so we can see what the major engine sections are for. We'll call it our Simplex Mark I jet engine. Picture the engine as being shaped like a big, long metal tube. This will form the outer case for our engine. Let's slice it right down the middle so we can look at the engine in cross-section. A jet engine literally lives on air. It breathes huge volumes of air per minute. It draws air slowly in the front of the engine and jets it out the rear at a high velocity, thereby producing thrust. It does all of this by burning a combustible mixture of fuel and air. So with that in mind, the first thing we'll install is the burner section. Metal lines bring fuel into the engine, and specially designed nozzles turn the stream of fuel into a fine spray, so it will mix thoroughly with the air. Add igniter plugs, somewhat like the spark plugs in your car. When they spark, we have ignition, and then continuous combustion. Once ignited, combustion continues as long as fuel is supplied. The hot expanding gases escape out the rear of the engine. Now we have the beginnings of what we need for our thrust equation to work. We have a mass, mostly air and a little fuel, and the burning process accelerates the mass. But that's just the beginning of the story. Next, we need a compressor. we'll reshape the engine case to accommodate one that is made up of several stages. Each stage looks something like a glorified blade assembly from an electric fan, except that our compressor stage has many small, short blades mounted around the edge of a central disc. If we install it right here, we'll have the first stage for our compressor. Now, put in a second, third, and fourth stage. Bolt them all together so they'll rotate as one unit, and we have a four-stage compressor. Rotating at high speed, it draws air in from the front and compresses it. Stage by stage, it forces the air to flow into a progressively confined space until finally it delivers high-pressure air to the burner section. Why have a compressor? To force huge quantities of air through the engine, to provide a big M in our equation. And as this high-pressure air rushes out of the compressor, it contributes to the A. And with air under high pressure, we can burn more fuel, release more heat energy to get more power, and do it efficiently. Now, we need to find a way to turn the compressor, to rotate it at high RPM. We'll do that job with a turbine. Think of a turbine stage as having a disc and blades, much like the compressor. Only the materials are much tougher back in this very hot section of the engine, and the blades are shaped differently for the job they'll have to do. We'll install a single-stage turbine right here behind the burner section. Then, we bolt in a shaft to connect the turbine directly to the compressor so they will rotate together at the same speed. The secret here is that the high-velocity gases from the burner flow past the turbine blades, causing the turbine to rotate like a high-speed windmill, thereby causing the compressor to rotate. Does this have any effect on our thrust equation? You bet it does. The turbine, by extracting so much energy from the hot escaping gases, decelerates the flow of gases a great deal, which reduces the A. Can't be helped though. We need the turbine to drive the compressor. By the way, if anyone tells you that a turbojet engine has only one main moving part, just say, sure, if you mean the combined compressor, turbine, and shaft. You're right. Before we move on, we'd better install an inner case in the burner section to isolate the turbine shaft from the combustion area. Next, we'll change the shape of the tube to form an exhaust duct that will provide a smaller opening, a nozzle at the very end. Remember how the nozzle on your garden hose works? When adjusted right, it puts out a long, high-speed stream of water. That's how the exhaust duct works. Because of its shape, it speeds up, accelerates the hot gases just as they leave the engine. That increases the A in our thrust equation to make our machine perform as a jet engine. By now, I'm sure you realize that air doesn't flow through the center of this tubular-shaped power plant. Rather, it flows through the annular space in the compressor, burner, and turbine sections. From there, it all joins together in the exhaust duct. With that understanding, we can now add the final touches to our engine. Let's put an inlet section on the front. The stationary vanes and nose cone will streamline the flow of air as it enters the compressor. And we'll add a tail cone behind the turbine to smooth the flow of gases in this area too. Now, our engine is in pretty good shape, but we have a design problem to consider. See all that flame passing across the turbine blades and into the exhaust duct? That won't do. It's inefficient and awfully hard on the parts. We'll solve that by making two changes. Watch what we can do. First, we'll reshape the inner case in this burner section like this. Second, we'll reshape the outer case like this. Now we have created the diffuser section of the engine. And look what it does to the path for flowing air and gases. Air leaving the compressor flows into an enlarged space, which slows the air down. This permits plenty of time for combustion to take place in the burner section where it ought to be. Notice, too, the outlet of the burner section. The gases leaving the burner are squeezed back into a more confined space, speeding the gas back up again as it flows into the turbine. Now our Simplex Mark I is complete and ready to go with all its major sections: inlet, compressor, diffuser, burner, turbine, and exhaust duct. An engine of this type is often called a turbojet, and you can see where it gets its name. Turbo. It utilizes a turbine, and jet. The exhaust duct jets the hot gases out through the nozzle at high velocity. But then, many people call it a gas turbine engine, because it functions with a turbine that is driven by hot gases, rather than steam or water as in some other power systems. Is a turbojet engine really this simple? Well, so far we've studied the major sections of the engine, but within those sections are more parts and features that need to be understood. So we'll go to something more realistic, a schematic of a typical turbojet engine. Taking first things first, we'll start at the front and work our way through the engine until we get to the exhaust nozzle. So, how do we get the air to enter the engine smoothly and without turbulence? We do it with a well-designed inlet section. It's a relatively simple stationary section. The outer case, inner case, and inlet guide vanes are the main structural parts. It has to be fairly rugged, though, because the bearing that supports the front of the compressor is mounted within the inner case. The nose cone also contributes to the smooth flow of incoming air. Note that the inlet guide vanes have a cross-section that is airfoil shaped. We'll find many airfoil shaped parts throughout the engine. Some are shaped like the wing of a plane. Others are just streamlined shapes. They're all designed to make the airflow react in some way. The inlet vanes have a slight twist to turn the incoming air at an angle so that it will enter the rotating compressor efficiently. Remember, the compressor is rotating at high RPM. We're beginning to see the jet engines have a language all their own. Part names, operating terms, slang expressions, acronyms, abbreviations. I'll be careful to use the right language, and will point out significant terms as they come along. For example, RPM. We all know that means revolutions per minute. But IGV? The abbreviation for inlet guide vane. Now, for the compressor and the big job it has to do. Draw in huge volumes of air. Compress it to 250, maybe 300 pounds per square inch or more. Tolerate temperatures of 600 or 700 degrees Fahrenheit. Withstand the centrifugal force created when it rotates at high RPM. And above all, handle the air smoothly, without turbulence, as it does all these things. Our Simplex engine had only a 4-stage compressor rotating within a tubular case. A real compressor is a bit more complex than that. The compressor actually has two major components: the rotor, the rotating part, and the stator, the stationary part. When combined, they form the complete compressor assembly. Let's look at the makeup of the rotor first. It's shown here standing vertically with the front resting on the workbench. The rotor is made up of several stages which are numbered from front to rear. With the rotor disassembled, the major parts are laid out for display. You can see that each stage is comprised of a disc with many blades fastened around its outer rim. Notice that the discs are open at the center to reduce their weight. Flanges on a disc like this, projecting forward and rearward, provide proper spacing between the discs. The blades are retained in dovetail-shaped slots. They fit rather loosely when cold, but during operation, with temperature up to normal and centrifugal force tugging at them, they fit snugly in place. The number of blades, their size and their shape varies from stage to stage because each stage has a slightly different job to do in the overall scheme of compressing the air. See that wing-like shape I spoke of? And notice how thin the blades are, especially out toward the tip. One very obvious point: the longest blades are in the front, the shortest at the rear, because the air is being packed into a progressively smaller and smaller space. Look how short and small they are in the last stage. However, in some of the forward stages, the blades are so long that they require mid-span shrouds to provide blade-to-blade support. This prevents blade vibrational problems. With the discs all bolted together, they form the complete rotor that rotates as one unit. Hubs at the front and rear are supported by bearings. As you can imagine, the compressor rotor must not be out of balance. Individual rotating parts, the discs and hubs, are first balanced. Then, each disc with its blades installed is balanced. And finally, after assembly, the complete rotor is carefully balanced. Now back to the stator, the stationary element of the compressor. The stator is also built in stages. Each stage consists of an outer case, inner shroud, and many airfoil-shaped vanes. There's that word again. You can see the wing-like contour of the vanes where they are attached to the outer case. A stator stage fits behind or downstream of each rotor stage. For example, the first stage rotor and the first stage stator, and the fourth stage rotor and stator. A stator stage has a twofold job to do. First, to receive the air from the rotor in front of it and redirect it at the proper angle into the rotor behind it. Second, to diffuse the air as it passes through these vanes, slow it down without losing any of the pressure being developed. Because of the stators, we find that the air doesn't swirl round and round as it is compressed. In fact, it flows just about straight through. Which brings up another term we ought to remember. This is called an axial flow compressor because the air flows parallel to the axis of the compressor. For the same reason, we refer to this type of power plant as being an axial flow turbojet engine. To maintain this axial or straight-through airflow, it is important that the air doesn't circle back around the tips of the blades and vanes. There are two important features to prevent this. The rotor blades operate in very close proximity to the surrounding stator case, and the stator inner shroud forms an air seal with the spacer that fits between discs. The last stage of stators, called the compressor exit vanes, directs the air straight back into the diffuser section. These vanes are often located in the diffuser case rather than in a separate stator case. The stator cases, when all joined together, form the stator assembly, which is the main strength, the backbone of the engine in this section. Now, how much air pressure will the compressor develop? Well, if it increases the pressure of the incoming air by 20 times, we say it has a pressure ratio of 20 to 1. With a ratio like that operating at sea level, it would boost the incoming air to almost 300 pounds per square inch. Compressors today have pressure ratios of 20 to 1 or better. Another point. The highest pressure within an engine of this type is always at the compressor exit. Okay, next up for discussion is the diffuser section. It's made up of an outer case and inner case which are connected by several streamlined struts. It's very simple in its design, but it has important aerodynamic and structural roles to play. Compressor air flows through the annular space between the outer and inner cases. But notice the shape of this passage. This brings us to another law of nature that's put to use in jet engine design. When air flows through a convergent duct, cone-shaped like this, it increases the velocity of the flowing air, speeds it up. A divergent duct has just the opposite effect, slows it down. The flow path in the diffuser is divergent. Air leaves the compressor at the correct pressure, but at a velocity that is too fast for complete burning in the combustion section. So the diffuser has the sole purpose of slowing the air down to an acceptable speed. Structurally, the diffuser must be good and tough. The outer case forms a continuation of the complete engine case. The inner case houses the bearing that supports the rear of the compressor rotor. The diffuser struts, in addition to being structural members, straighten the airflow on its way to the burner section. The burner section has the more official designation of combustion section, so we'll label it just that. Remember, its job is to create rapidly expanding hot gases, all rushing toward the rear of the engine for two purposes: to turn the turbine and then jet out through the exhaust duct. The main structural members are the outer case and the inner case. Again, the annular space between is where the action takes place. However, we don't just burn fuel in that open space like we did in our Simplex Mark I. We need a way to regulate the burning process to provide truly efficient combustion. We do this by burning the mixture of fuel and air within several individual burner cans. They're placed side by side to form a circle of burner cans within that annular space. The number of burner cans varies for different engines. We'll say that our typical engine has 8. A cluster of fuel nozzles supplied by a fuel manifold introduces fuel into the front of each burner can in a spray pattern for rapid and thorough mixing with the air. Combustion is complete and the flame is confined within these burner cans. But even with the use of special metal alloys, the cans have to be specially designed to prevent the metal from being destroyed. The air, which of course is essential for burning, flows from the diffuser into the annular space and then enters each burner can through a myriad of holes. The holes vary in size, shape, and spacing, so that the actual flame is centered in the middle of the can by the incoming air and does not actually touch the metal walls of the can. The temperature of that flame, by the way, is 3,500 degrees Fahrenheit or hotter. About 1/4 of the air is directed into the flame area for combustion. The other 3/4 is directed along the wall of the burner can to provide a blanket of cooling air. Burned and unburned air mix together at the burner can exit, substantially reducing the temperature. Ignition to start the burning is provided by igniter plugs in 2 of the burner cans. The burner cans are interconnected by small flame tubes, so that during the starting process, flame started in 2 of the cans develops rapidly in all the others. Once started, burning is continuous during engine operation, and it's not necessary for the igniters to continue firing. The burner cans are supported at the front by brackets attached to the 8 diffuser struts. They are supported at the rear by an outlet duct that provides a transition from 8 circular openings at the front to a single annular opening at the rear. Notice that the outlet duct forms a convergent flow path. This causes the rush of exhaust gases to accelerate even more as they flow into the turbine section. And now we've arrived at the hottest section in the whole engine. The total output of the burner impacts directly on the turbine. Temperatures here may well exceed 2,000 degrees. If the best in metallurgy was ever needed, this is the place. So let's look closely at the makeup of the turbine section. The burner case and now the turbine case continue to form the outer shell strength in these areas. And by the way, you can always recognize a turbine case because of its unique shape. See how it overlaps the burner section? That wasp waist shape provides the convergence we need at the burner exit, and the enlarged diameter at the rear, as we'll soon see, accommodates the size of the turbine rotors. Now, we've said it before, the turbine has a single-minded purpose: to rotate the compressor so it can do its job. And like the compressor, it also has a rotating and stationary element. The turbine rotor spins like a glorified windmill as the exhaust gases flow past. Fact is, it extracts about 3/4 of the hot gas energy just to drive the compressor. Being joined to the compressor by the long turbine shaft, the turbine and compressor both spin at the same high RPM. An engine like this will run at about 10,000 RPM or higher. Each rotor stage, or turbine wheel, as they are sometimes called, is made up of a disc and blades much like we found in the compressor. The unusual shape of the blades, especially the great curvature, is designed to convert the energy of the gas flow into rotational power. You will find that the longer turbine blades frequently have tip shrouds to prevent blade vibration problems, and also to reduce gas flow leakage around the tips of the blades. Some turbine blades, because of the tougher and therefore heavier materials required, are retained in the disc using a fir tree base rather than the dovetail shape we spoke of before. Now, how about the stationary element of the turbine? Each stage consists of many vanes attached to the turbine case. These nozzle guide vanes, as they are called, precede each rotor stage. Nozzle guide vanes? Good name for them. They guide the hot gases at the most forceful angle against the rotor blades. And since the openings between the vanes form a series of small convergent nozzles, they speed the gas up as it flows against the rotor. You'll hear people speak of a complete assembly of these vanes as being a turbine nozzle, Our engine then has a first stage turbine nozzle and a second stage turbine nozzle. Are you beginning to see that while the turbine looks similar in some respects to the compressor, it is really quite different? The compressor is forcing the air pressure to rise by packing it into a smaller and smaller space. The compressor can only do this in small, easy steps. Our typical engine has 9 stages. The turbine, however, is permitting the hot gases to escape, exchanging this source of energy for rotational power. Turbines can do this in large steps. Ours has 2 stages. Turbine materials are different too. They must be tougher and highly heat resistant. In many of our engines, the forward stages of the turbine have air-cooled blades and vanes so they can tolerate these extreme temperatures. Relatively cool air is routed from the compressor through special passages and then right through these hollow blades and vanes. The escaping air then joins into the main stream of exhaust gas. Have you wondered why the second stage turbine is larger in diameter than the first stage? No matter how many stages in a turbine, each succeeding stage is larger because it has less hot gas energy to work with. Put simply, the windmill has to be larger because there is less breeze to turn it. 2 more points and our turbine is complete. Turbine exit vanes straighten the airflow as it passes into the exhaust duct and provide the structure to support the turbine rear hub bearing. And just as in the compressor, you'll find the need here to prevent flow leakage around the tips of the blades and vanes. Special air seals and minimum blade tip clearances are part of the turbine scheme too. Let's take a final look at the turbine by reviewing the stage numbering. First stage nozzle, first stage rotor, second stage nozzle, second stage rotor, and exit vanes. Last comes the simplest part of the engine, the exhaust duct. Because of its convergent shape, it accelerates the gases to the highest possible velocity just as they leave the engine. Because of this jet effect, the final opening in the duct is called the exhaust nozzle. The nozzle is sized and measured carefully in square feet of opening to provide the exact gas velocity required to produce a specified thrust. A tail cone streamlines the inner boundary of the gas flow. And now, our engine is complete. We've covered a lot of ground in short time, so let's summarize by reviewing some of the highlights. The tubular outer cases of the engine, when all joined together at their bolted flanges, form the main strength of the engine. The one main rotating part of the engine is the combined compressor, shaft, and turbine, all rotating at the same RPM. This huge mass of rotating machinery is supported by bearings in the inlet case, diffuser case, and turbine case. Air at atmospheric temperature and pressure enters the inlet at a relatively low velocity. The inlet section ensures a smooth entry of air into the first stage of the compressor. The compressor draws in a huge mass of air and compresses it to a high pressure. The diffuser slows the air down while retaining the high pressure. The burner increases the velocity of the air by adding the energy of burning fuel. The turbine extracts energy from the hot gases as they rush by and converts it into rotational power to turn the compressor. The exhaust duct and nozzle boost the gases to a final high velocity. So you see, air and gas don't flow through the center of the engine. Rather, they flow through the annular space in the various engine sections. Now let's take a final look at our thrust equation. Did it work? You bet it did. The compressor assured us of a huge mass of air, and the total engine created a final high velocity at the exhaust nozzle that gave us the acceleration we needed. We'll have to leave it up to our design engineers to pick it up from there, to account for the fuel passing through the engine and other important factors needed to arrive at a real and accurate thrust value. The engine we've been studying is typical, but there are some variations in the design of turbojet engines you can watch for. Here are 5 common ones you should know about. First, to build more efficient engines, we need higher compression ratios. Often, this requires more stages in the compressor. Suppose we change our 9-stage compressor to 16 stages and add the necessary turbine stages to power it. That looks good, but the problem is all 16 stages are rotating at the same RPM, and that would result in inefficiency. The big long blades up front are trying to grab a lot of air and pull it in. The smaller, shorter blades toward the rear are working under pressure and trying to create even more pressure. This results in poor engine performance and would likely result in an operating problem called compressor stall. This is a situation where some of these airfoil-shaped blades actually quit pumping air. More on that in a moment. The solution to this is a concept called the dual rotor engine. It has 2 mechanically independent rotor systems, 2 compressors, each driven by its own turbine. The low-pressure compressor draws in the atmosphere and starts the compression process. It's driven by the low-pressure turbine. It gets its name from the lower pressures that make it turn. The high-pressure compressor boosts the air up to maximum pressure. It's driven by the high-pressure turbine, so called because of the high pressures delivered from the burner that make it revolve. You can see how the one turbine shaft revolves independently inside the other. Now, what does the dual rotor design do for us? It has many advantages. For openers, the 2 compressors operate at different RPMs, so that each runs at its best, most efficient speed. Because it handles the airflow more effectively, higher compression ratios are attainable and stall problems are greatly reduced. Structurally, the individual parts, vanes, blades, discs, and so forth, follow the same design as a single rotor engine. However, this has one additional major part: the intermediate case. A rugged structure that joins the 2 compressors and provides bearing support for both. The struts straighten the airflow as it passes through. Obviously, the bearing system must be more elaborate in an engine like this. The one shown here has 8 bearings. Before we move on, let's resolve a point of terminology on this dual rotor engine. Here's a situation where we find that people in the jet engine industry have 3 names for the same thing. The low-pressure compressor is also called the low compressor or front compressor. No confusion. The terms make sense. The high-pressure compressor is also called the high compressor or rear compressor. The same trend in language also follows for the turbine. And you'll find the dual rotor concept itself called by other names: twin spool, dual axial. Take your pick. They all mean the same thing. Since most of our engines today have a dual rotor, we'll use this type in illustrations coming up. Let's digress for a moment and talk about compressor stall. What is it? It's a momentary condition. Most often where airflow over the compressor blades becomes turbulent. The blades actually stall, just as the wing of an airplane might if it approaches the air at too great an angle. Air no longer flows back through the compressor as it should. In fact, the air does a complete turnaround. While the condition exists, the normally higher pressure at the rear of the compressor causes the air to actually flow forward. It can happen to one blade or many, to one stage or several stages, to one compressor or both. The result of compressor stall is engine surge. Airflow through the entire engine is momentarily disrupted. Vibration is likely. Metal temperatures climb for lack of air cooling. Combustion is irregular, and loud bangs may be heard. Flameouts can occur. Sound mysterious, like a demon that intrudes in the night? Not really. Compressor stall is an inherent potential problem in all high-performance jet engines. Compare it with the piston engine in your car. It has an inherent but different problem. With the wrong grade of gas, it will ping. Maybe you call it knock or detonation. The point is, all gasoline-powered four-cycle engines are prone to do this. With the high airflows and high pressures demanded of a modern-day compressor, compressor stall is an ever-present characteristic that our designers must deal with head-on. It can be caused by conditions that drastically disturb the smooth flow of air through the compressor. Unusual aircraft attitude, flying in turbulent air, ice buildup in the inlet, jam acceleration, things like that. What do we do about it? How do we build high-performance compressors and yet avoid this condition? We do a number of things. The dual-rotor compressor, we've already discussed that, decreases the engine's susceptibility to stall a great deal. Compressor air bleeds provide another answer. Most all of our engines have these. Air bleed ports release part of the compressed air overboard during those periods of operation where stall is most likely to occur. This relieves the bottleneck to airflow that can cause the stall. The bleed ports and their controlling valves are usually located between the low and high compressors. They are open while starting the engine to let it gain RPM more easily, and they're closed during high thrust operation. During other periods of performance, acceleration, deceleration, low thrust levels, and so forth, the bleed valves are scheduled to open or close automatically, depending on operating conditions. Another solution on our later engines lies in the design of the compressor stator vanes. Up to now, we've seen stator vanes that are manufactured at a fixed angle. Variable angle stator vanes, stator stages in which the vanes can be angled a little more, a little less, tailor the airflow and pressure to avoid stall situations. A sync ring controlled by hydraulic actuators synchronizes the movement of the vanes. They're used in the forward stages of a compressor, and it's common to find a similar arrangement used for the engine inlet, where they are called variable inlet guide vanes, VIGV for short. For example, on our typical engine, we find them used at the inlet, the first two stages of the low compressor, and the first two stages of the high compressor. These variable stators are frequently used in conjunction with an air bleed system to prevent compressor stall. And like the air bleeds, they are scheduled to function automatically as engine conditions signal the need. So three of these variations in design, the dual rotor, overboard air bleeds, and variable angle stator vanes, have to do with that all-important, smooth, steady flow of air through the compressor. Another major difference in our family of engines is in the combustion section. As you'll recall, our typical engine had multiple burner cans, 8 of them, where the burning actually took place. Our more recently designed engines have an annular burner, one continuous circular burner. You can recognize many of the design features used in the multiple can setup. The brackets for attachment to the diffuser case, the fuel nozzles, evenly spaced around the forward edge. The holes for combustion air and cooling air are used in the same way. With the annular burner, you look for them on the outer surface and inner surface. But notice that the design eliminates the need for the separate, rather complex outlet duct required for the 8 burner cans. Advantages compared to the multiple can setup? Smaller, lighter. It provides more efficient combustion, and yet it takes up less space. In some of our later engines, the annular burner requires so little room that the diffuser and burner cases are combined as one. Now, the last of these design variations we want to cover provides us with an entirely different type of compressor. Rather than the multiple stage axial flow type that we've illustrated so far, this is a single stage centrifugal flow compressor. The impeller rotates at high RPM within a closely fitting case. The incoming air, trapped between the vanes of the impeller, is pressurized as it is slung outwards and packed into the confined space at the rim. From there, it flows through the diffuser and into the burner. Jet engines seldom use centrifugal compressors alone. Usually they are used in combination with the axial flow compressor. In this engine, for example, air is first compressed by a 3-stage axial flow compressor and then compressed further by a single-stage centrifugal compressor. As you have just seen, jet engines do vary in design, and that's mainly because of the customer's requirements and the mission an aircraft is destined to fly. You see, the design of each engine is tailored to meet the demands of a specific type of plane. Now that we understand the principles used in our typical jet engine, we're ready to see how this thing we call a gas turbine engine can be applied in different ways. You see, the combined sections of the engine that really generate the power, the compressor, diffuser, burner, and turbine, are called the gas generator. The gas generator not only functions on its own, but it generates hot exhaust gases, energy in the form of heat and pressure that can be used in a variety of ways. We've already seen that the addition of a convergent exhaust duct turns it into a turbojet engine. Let's take the gas generator now and add the necessary parts to build an afterburning turbojet engine. The afterburner is, in effect, one huge burner can where we burn more fuel to accelerate the gases to an even higher rate, to make the A in our thrust equation much larger. Fighter and interceptor aircraft require that their engines produce more than their normal power for short periods of time. Takeoff, climb, maybe a burst of speed for combat. Well, the afterburner serves this need. It provides thrust increases of 50% or more. The amount varies with different engine models. However, they're used only for short periods of time, because they double or triple the engine's fuel consumption while they're in operation. The afterburner, called AB for short, is a large addition to the engine, but it's not complicated. First off, it requires a diffuser case. In combination with the tail cone, it provides a divergent flow path to slow the exhaust gases down a bit prior to combustion. Just as in the gas generator, the flow of gases into the afterburner has to be slowed to the extent that complete burning can take place within the afterburner. The afterburner duct, or main case within which all combustion takes place. Notice the diameter and length of this thing. It's the largest single component in the engine. And on engines like this, you'll find a variable area exhaust nozzle, one that can be scheduled to automatically vary its opening, larger or smaller, to help create the amount of thrust that the pilot calls for. Circular fuel spray rings, several of them, each with built-in fuel nozzles. They're scheduled so that with one or two rings providing fuel, the pilot can get partial power from the afterburner. With all the rings supplying fuel, maximum power from the AB is obtained. And of course, with this condition, the total engine is producing its maximum power. The flame holder. It sits right in the path of the gases as they enter the combustion area. Its purpose? To create turbulent gas flow. Maybe that's why it's the ugliest part of the entire engine. After looking at so many smoothly contoured and airfoil-shaped parts, this is truly a strange-looking sight. It's a network of annular and radial gutter-shaped pieces that slow the gases down even more and provide thorough mixing of the fuel and air so the flame will be held within the afterburner and not be blown out the exhaust nozzle. The igniter plug is frequently mounted right in the flame holder. As in the gas generator, the high-intensity spark is required just long enough to get the fuel and air mixture lit. After that, the flame is continuous and self-sustaining. The liner has a rough and tumble job to do. In fact, it serves a dual purpose. A portion of the exhaust gases, cooled considerably by the time they leave the turbine, flows between the duct and liner and then passes through thousands of tiny holes in the liner and then into the combustion area. This confines burning to the center and helps keep the AB duct cool enough to survive the extremely high temperatures. Its second purpose is to reduce noise. The AB makes a howling or screeching sound. In fact, this part is often referred to as the screech liner because it is designed to do an acoustical job by reducing the amount of noise the afterburner creates. And there you have it. The afterburner serves the military pilot well. When he positions his throttle between idle and intermediate, the gas generator alone delivers the thrust he needs. The afterburner merely acts as a long exhaust duct with the exhaust nozzle serving its usual function. When the pilot wants more thrust, from intermediate up to max power, the gas generator continues to deliver its utmost, and the AB cuts in and contributes to the total thrust produced. Fuel flow from the spray rings and the exhaust nozzle opening vary according to the amount of thrust called for. Okay, let's look at a second way of applying the gas generator for propulsive force. Suppose you managed an airline and your air routes were all milk runs, up and down, out of small fields all the time. You need engines that will provide quick takeoff and rapid climb out. What's the best engine for that? A turboprop, a gas turbine engine that turns a huge propeller. Notice that the prop is driven by the low-pressure turbine, but not directly. The low turbine drives the low compressor. The low compressor drives a reduction gearbox, and the gearbox rotates the prop. A gear reduction of about 10 to 1 is typical. With that, the engine might be turning at 10,000 RPM and the prop would turn at 1,000 RPM. You see, props can't be turned at real high RPM. If they did, those long blades would exceed the speed of sound, above which conventional propellers operate inefficiently and are subject to stress beyond their limitations. And notice, too, that the low-pressure turbine in this engine must be relatively larger or have more stages because it has more work to do. It has to extract enough of the hot gas energy to rotate the low compressor and the prop. A turboprop gets about 90% of its propulsive power from the prop and 10% from the jet effect of the exhaust nozzle. And by the way, a propeller produces thrust using that very same thrust equation, only this time the prop is handling a huge mass of air but imparting a relatively small acceleration. That's why when comparing it to a turbojet engine, it has spectacular acceleration and takeoff characteristics and proves to be more efficient at aircraft speeds of 400 miles per hour or less. However, it doesn't do well at higher altitudes where air is too thin for the prop to perform at its best. What we've just said about thrust is true, but you won't find turboprops rated in pounds of thrust like the turbojet engine, because most of its power is extracted from the shaft rather than the jet exhaust. It is rated in shaft horsepower, SHP, or sometimes equivalent shaft horsepower, ESHP, which is the power from the shaft plus the equivalent horsepower gained from the small jet effect of the exhaust. Let's consider a type of engine that performs right alongside the turbojet in terms of high aircraft speeds and high altitude performance, and yet provides a rapid takeoff and climb that the turboprop is known for. This is the turbofan engine. Is it obvious what the designer was trying to do with this one? Sure. It's a hybrid, the best of two worlds. It has all the elements of a turbojet, but it's also a little like a turboprop in that it has many fan blades incorporated as part of the front compressor. This provides a prop-like thrust without having the complexity and weight of a propeller and gearbox. Take a closer look. The forward stages of the low compressor have extra long blades and vanes, and they serve two distinct purposes. The inner portion of the blades and vanes function as part of the low compressor in the gas generator. The outer part serves as a multitude of miniature propeller blades, properly called fan blades. They draw in an additional mass of air, accelerate it, and then expel it from the exit of the fan section, thereby producing a separate additional source of thrust. It takes a lot of power to rotate this low compressor with the added fan blades, so the low pressure turbine must be large enough, have enough stages to do the job. So the gas generator with its jet nozzle contributes to the overall thrust, and the fan contributes too. How much? For a ballpark figure, let's say 50-50. But it's hard to generalize because the amount of thrust generated by the fan depends on its size and the number of stages. Some engines have single-stage fans. Our schematic shows 2. Others have more. And this brings us to the term bypass ratio, the ratio of fan air to gas generator air. Our PW2037 commercial engine has a bypass ratio of about 6-to-1 because its fan handles a great share of the air. If our schematic appears to show that the fan and gas generator handle equal amounts of air, then our engine has a bypass ratio of 1-to-1. The fan exhaust is handled in different ways, depending mainly on the needs of the aircraft installation. On some, the short fan case shown is all that is needed. And on others, a long fan duct encircling the whole engine carries the fan air back to where it joins with the gas generator exhaust. In this configuration, the engine is referred to as a ducted turbofan. Our commercial JT8D is built like this. Now, if we develop this engine one step further, we'll have today's typical military engine, the augmented turbofan. The augmenter is nothing new to us. Yesterday's afterburner is today's augmenter. The same thing. They just changed names on us. The terms are interesting, though. Afterburner describes what it does. Augmenter tells us why we have it. From our discussion on the afterburner, I'm sure you'll recognize the fuel spray rings, the flame holder, the liner, and so forth. Look how the concept is applied to our fan engine. When running at throttle settings up to intermediate, the exhaust gases and fan air join together downstream of the turbines and exit through the exhaust nozzle. The engine performs as a ducted turbofan. Above the intermediate power setting, the augmenter cuts in and provides infinite variation in power up to maximum. The big difference between this engine and the afterburning turbojet is that the turbofan gets its oxygen for burning from two sources: the unburned air in the gas generator exhaust gases and the supply of fan discharge air. With this design, the fan provides an excellent source of relatively cool air to reduce augmenter case temperatures and permit the burning of greater quantities of fuel, the addition of more heat energy to get more thrust. The exhaust nozzle? Yes, it is shaped differently than on our previous illustrations. Remember, we discussed how convergent and divergent shapes influence airflow. The convergent areas accelerate flow, and the divergent decelerate flow. Well, that's true with air or gas that is flowing subsonically, below the speed of sound. Flow through the gas generator is subsonic, and we've seen how these principles are applied. Now, it may sound strange, but this principle reverses itself when air or gas flows above the speed of sound. A convergent duct slows the air down, and a divergent duct speeds it up. And now we can see how our designers put this knowledge to work using the CD nozzle, the convergent divergent nozzle. Velocities are below the speed of sound, Mach 1, until they reach the exhaust nozzle. To gain the greatest possible acceleration through the nozzle, the convergent section brings the gases up to Mach 1, and then the divergent portion accelerates the gases even more, above Mach 1. The same understanding of airflow is used in designing the aircraft inlet, that part of the airframe that guides air into the engine. With the aircraft flying at Mach 2, 2 times the speed of sound, you may wonder why air doesn't ram itself through the engine at Mach 2. If it did, it would be destructive. The engine wouldn't tolerate that. So a CD inlet is used, in this case, to slow the air down. The convergent section slows the air from Mach 2 down to Mach 1 at the throat, and the divergent section slows it even more before it enters the engine. Just as the exhaust nozzle is scheduled to vary the size of its opening for varying amounts of thrust, the aircraft inlet is often designed to vary its configuration to accommodate different inlet velocities. Okay, one more family member you should know about. This application of the gas generator is a blood relative of the engines we've seen so far, but it doesn't have to fly to earn its keep. This is the turboshaft or free turbine engine, the one that is used for a variety of power requirements. This time, we mount a free turbine just downstream of the gas generator turbine. By free, I mean it's free to rotate independently of the gas generator. Picture it as if it were a windmill, free to spin in the blast of hot gases. The output shaft, connected directly to the free turbine, makes the rotational power readily available for work to be done. The exhaust gas, its energy pretty well spent in driving the free turbine, is directed out and away from the installation to any convenient location. These engines are rated in shaft horsepower, like the turboprop. Can you imagine 40 to 50,000 horsepower available in one package? And they can be used as a power source for a variety of applications. Turning huge electrical generators, rotating natural gas pumps. And by the way, our engine designs can be adapted to run on a variety of fuels, including natural gas. For powering boats and ships, and for airborne purposes too. They're used to power helicopters, and when the output shaft drives a prop for conventional aircraft, it becomes another form of turboprop. Turbo shaft engine design varies. The output shaft doesn't necessarily have to project out from the exhaust end of the engine. In this version, the free turbine shaft revolves within the gas generator shaft so that the rotational power of the free turbine is available at the front of the engine, as it might be for a turboprop application. Well, you can see now that the gas generator is a very versatile power source. It is the heart of every engine we build, whether it be turbojet, turboprop, turbofan, or turboshaft. Up until now, we've been dealing with bare bones engines, just plain engines with no way to run them or control them. Maybe you've seen all the plumbing, wiring, valves, and so forth on the outside of the engine. Now, we'll find out what they're for. For a comparison to what we'll be talking about, look under the hood of your car. You'll find a carburetor, alternator, power steering pump, air conditioning compressor, etc. Well, the jet engine needs its accessories too. Some similar to your car and others a good bit different. Let's find them. A gearbox mounted below the engine provides the rotational power for most of the accessories that must be driven. The gearbox gets its rotary power from the compressor. As the compressor rotates, a pair of bevel gears and tower shaft transfer the motion down to the gearbox. Then the gear train within the gearbox comes alive to provide rotary power to each accessory drive pad. What kinds of accessories are driven? Fuel pump, oil pumps, hydraulic pump, electrical generator, things like that. And on some, a tachometer generator and fuel control are linked to the gearbox. But not all accessories are driven mechanically by a gearbox. Some accessories can be driven by compressed air from the compressor or diffuser section of the engine. For example, one of our engines has an afterburner fuel pump that incorporates a small air turbine. It works on the same principle as the gas turbine in the engine itself. Compressed air from the diffuser section flows through the air turbine, and that causes the pump to rotate. On other engines, air pressure is used as the muscle power for controlling the opening of the variable area exhaust nozzle. Compressor air is also used to drive accessories on the airplane. You may hear of a customer air bleed, for example, to power an air conditioning system. However, we can't overdo this business of robbing compressor air for such purposes. We have to limit it to a small percentage of the engine airflow. More than this would reduce engine performance too much. Okay, now that we have found ways of powering the accessories we need, let's look very briefly at 7 major engine systems. First of all, the lubrication system. And what do we have to lubricate? The engine bearings. The bearings and gears for the tower shaft and the gears within the gearbox. The oil used in jet engines is not your usual 10W30 type you might put in your car. It takes a special synthetic oil to withstand the extremes from the coldest spots around the globe when the engines are shut down to the high temperatures created when operating at max power. When you walk up to an engine, the only obvious part of the lube system is the oil supply tank. usually a saddle-shaped affair to fit the contour of the engine. It's mounted alongside the compressor section, up forward where it's not too hot. Those metal lines you see carry the oil from the tank into the guts of the engine, to those bearings and gears, and then back to the tank. But during this continuous operation, several other components in the system get into the act. A pressure pump and pressure regulator to ensure an adequate supply of oil at each lubrication point. Scavenge pumps, that's a good name for them. They grab the oil from each of the lube points after it's done its job and send it back to the supply tank. Oil coolers remove the heat from the oil. It gets mighty hot during that round trip, especially to the bearings back in the turbine area. Oil filters clean the oil, remove foreign particles. Add a special drain port so we can inspect samples of the oil for contamination periodically, and our system is complete. Second, the fuel supply system. To start with, when you fill up your car, you pick regular or premium or maybe diesel. These are types of automotive fuels. When you hear of jet engines running on JP4, JP5, or JP7, these are different types of jet engine fuels, but they're not gasoline. Jet fuels are in the kerosene family. The aircraft stores the jet fuel, most often, in wing tanks. It also has boost pumps and filters to provide a clean, steady supply of fuel to our engine. The engine fuel pump, that's driven by the gearbox, receives the fuel and delivers it under pressure to the gas generator fuel system. An afterburning engine will have a separate pump for the afterburner fuel supply. Most likely, it will be the air-driven type we spoke of earlier. Third, many of our engines require a hydraulic system much like the brake system on your car. When you apply your brakes, hydraulic fluid under pressure forces the piston to move in the actuating cylinder for each wheel brake. In a very similar way, we use hydraulic actuating cylinders to move things on the engine. Remember those variable angle stator vanes? Hydraulic power can be used to set these at the right position. And the variable area exhaust nozzle? Some of our engines have hydraulic actuating cylinders to provide this movement. Unusual thing about our hydraulic systems, though, we don't use the regular automotive or aircraft hydraulic fluid that you might be familiar with. Instead, the hydraulic pump, driven by that gearbox, picks up jet fuel right from the wing tanks, and the fuel becomes our hydraulic fluid. Being a circulating type of system, the fuel is cycled right back into the fuel system and is eventually burned in the engine. The ignition system, number 4 in the list of systems we need. We spoke of the igniter plugs before. Always 2 plugs, redundant system in the burner section. The augmenter may have 1 or 2. An electrical generator, driven by the gearbox, is the usual source of power. Ignition exciters take this low voltage supply and boost it to provide the high energy spark we need at the igniter plugs. Fifth, we need a starter. We'll talk about how we start the engine shortly. The job of the starter is to get the high and low pressure rotors revolving up to a desired RPM. The starter is adapted to the gearbox and its power is applied up through the tower shaft and from there to the high rotor. As it rotates and draws air through the engine, the flow of air causes the low rotor to rotate. There are a variety of power sources for jet engine starters. Some are electric, like your car. Most are pneumatic. Air pressure, driving a small air turbine, is the motivating source. Number 6, we need instrumentation. The pilot needs enough gauges to tell him that the engine is operating properly and safely. things like rotor RPM, fuel flow and pressure, oil pressure and temperature, and that all-important EGT, exhaust gas temperature, to make sure the turbine isn't exposed to excessive heat. But additional instrumentation is needed for another purpose, as part of the scheme for controlling thrust. The heart of this system is the engine's fuel control. This is the seventh of our systems, and I saved it for now because it ties so many of the other systems together. The system for controlling thrust, with the fuel control calling the signals, is a very complex system because of the very great demands we put on aircraft and their missions. You see, in today's jet aircraft, the pilot can pay only little attention to his engine. His attention must be outside the cockpit as much as possible. For that reason, they don't give him a lot of knobs to pull, levers to twist, or switches to flip. Darn few. So the pilot's single main control over the engine operation is the power lever, or throttle. With this one lever, he commands the engine to provide the performance he calls for, and everything that happens in response to his request is automatic. And this is where the fuel control comes in. The pilot's power lever is linked directly, mechanically or electrically, to the fuel control. Now, the fuel control is a brain of sorts. Besides knowing what the pilot is asking for, it senses everything that's going on, and that's where the additional instrumentation is needed. From instrument probes at strategic points, it senses the pulse of the engine, the critical temperatures and pressures, and things like RPM and fuel flow. And moment by moment, it sorts all these things out and sets up the conditions by regulating other systems to give the pilot the thrust he has called for. On a typical afterburning engine, it schedules fuel flow to the burner section, fuel flow to the afterburner, variable area nozzle opening, the opening and closing of the compressor bleeds, and the position of the variable angle inlet and compressor stator vanes. The fuel control even schedules the igniters to fire when the pilot moves the power lever to start the engine. And when he pulls it all the way back for an engine shutdown, it shuts off the fuel. It's like having a genie at his command. All he has to do is ask. Okay, we've got enough to run the engine now. We took the bare engine and added 7 necessary systems. We have the power lever to operate it with and enough dials and gauges to keep track of its operation. One more point before we start it up, though. Take a look at the tachometer for engine RPM. There are some things that we ought to know here. You can expect axial flow engines to operate in the ballpark of 8 to 14,000 RPM, somewhere in there. You may find a tachometer for the low compressor, the high compressor, or both. In either case, they operate at slightly different RPM, with the low compressor running slower than the high. Take a closer look at the tach in the cockpit, and you'll find that it's not graduated in RPM, but in percent of full RPM. The jet aircraft industry agreed long ago they would go this route. This means that when the engine is running at the full RPM it was designed to run at, the gauge will read 100% RPM. With a readout like this, the pilot can speak in terms of an overspeed, the engine went to 103%, or the engine should idle at 52%. On our test stands, however, you'll find tachometers of both types, those that read in RPM and others that read in percent RPM. That business about the idle RPM is another interesting point. Jet engines don't idle slowly like automobiles. No, they idle at 40% RPM or maybe even higher. And one last point before we move on. Did I mention which way our engines turn? They all turn the same way. Viewed from the rear, Stand at the back of the engine and look forward. They turn clockwise, unless you have a digital watch, that is. Okay, now let's put our engine on a test stand and see if it will run. The cycle of events required to start a jet engine is the same on all engines, whether the engine is mounted on a test stand where separate actions may be required by the operator, or installed in an aircraft where everything happens automatically. In this sea-level control room, these engineers and stand operators monitor engine performance. Three things must occur in the proper sequence. First, we need airflow through the engine, and we get that by engaging the starter and bringing the rotor speed up to 10% RPM, then 15%, and then 20. Next, the igniter plugs are scheduled to start firing. And last, as the RPM continues to increase, the fuel is scheduled to burn flowing to the burner, and we get a light off. The engine starts to run. But we're not done yet. The engine is running at a low RPM, but not to a point where it will sustain itself. So the starter continues to be applied, and the combination of the starter and the engine power bring the RPM on up to its idle of about 60%. That's where the engine will sustain operation by itself. Then the starter is disengaged, and the starting cycle is completed. It's running now, and we can check it out. Does it require warm-up time? No way. Piston engines require warm-up time, but not jet engines. Once that fire gets lit in the burner, it heats up in a hurry, like it or not. Oh, that's not to say that every bit and piece of the engine reaches its operating temperature in a split second. They won't. Your friends on the test stand will speak of stabilizing the engine. To get accurate test data, they'll set the engine at the power setting they want and then leave it there for 3 or 4 minutes, maybe even more. So temperature effects will be complete. Then they check their data. And you'd be amazed at the expansion that takes place when a stone-cold engine is cranked up and then pushed on up to full power. Any doubt in your mind as to where the greatest expansion takes place? Sure. Back in the burner and turbine areas, and of course, the afterburner, especially when it's lit. If you work with the drawings or parts for these engines, it's interesting to watch for design features that permit the expansion and contraction when the engine is shut down, without causing buckling or fracture of the parts. Look at this burner can, for example. The front of it is firmly attached to the diffuser case, yet with flame temperatures of 3,500 degrees or more, it's going to expand like gangbusters. So it's designed so it can expand toward the rear. See how it mates with the outlet duct? How it can slide back and forth. And check this Z-band support for the afterburner liner. You can imagine how hot this gets when the afterburner is operating. If these supporting members were radial, like the spokes on a wheel, they would buckle when the liner grows larger from the heat. Instead, these Z-band pieces can give a little without breaking. While we have the engine running, let me show you what goes on inside the engine in terms of temperature and pressure. These are the numbers we might see if we ran our F100 engine, for example, at sea level on a standard day, quote unquote. I'll explain that one a little later on. First, let's look at internal pressures. Air enters the inlet at 14.7 pounds per square inch. That's the air pressure that you and I live in. The fan section, functioning as the low compressor, compresses it to almost 45 pounds, and the high compressor brings it up to about 360. Pressure drops only a little going through the burner section, but drops way down as the turbine converts the energy of the gases into rotational power, and it continues to drop as it flows through the afterburner and out the nozzle. Now, the temperatures. With air entering the inlet at 59 degrees Fahrenheit, it's a little over 1,000 degrees at the compressor exit. And that's just from compressing the air. The hottest spot in the gas generator, just behind the burner, or at the turbine inlet, the gases are over 2,500 degrees. We expect the temperature to drop as the gases pass through the turbine because the turbine extracts energy from the gases. And then temperatures zoom back up with the augmenter operating to over 3,200 degrees. Is it any wonder we're continually searching for the best in metals? And consider the exterior parts, the components, the wiring, the plumbing. This will give you an idea of what the trend of temperatures is on the outside of the engine. Cooler, sure, but now you know where the hottest places are and why they mount these exterior parts up around the compressor and diffuser sections, where it's not so darned hot. Let's get back to that business of testing our engines on a standard day. Remember, we said way back that the amount of thrust developed by a jet engine depends to a great extent on the amount of air the engine is handling, the mass of the air flowing through the engine. Well, it makes sense then that as the weather changes, the density of the air changes. Changes in barometric pressure and temperature change the amount of mass going through the engine, and therefore it changes the amount of thrust produced. Hence, with a low temperature or a high barometer reading, the engine will produce more thrust, and vice versa. The jet engine industry established 59 degrees Fahrenheit and 14.7 pounds per square inch as being a theoretical standard day for engine testing. But we can't sit around waiting for that standard day to happen. So our test engineers run the engines on any kind of day, and then mathematically correct the engine data to what it would be if it were run on a standard day. Now we can calibrate our engines in Nome, Alaska, West Palm Beach, Florida, or Timbuktu. Calibration? That's when we run the engine to see if it performs to specified standards. The environment has other effects on a jet engine too. A jet engine is like a giant vacuum cleaner, and it will suck in anything it can. Dust and dirt. If it builds up enough on the blades and vanes, it can hurt engine performance. With the aircraft running on the ground, rocks and debris on the runway get sucked in. If you leave a wrench laying in an aircraft inlet, in it goes. FOD, they call it, foreign object damage. The heavier objects can damage the engine, and jet engine people have an eternal vigil to make sure that does not happen. On our test stands, we install an inlet screen. They call it a FOD screen to prevent such damage. But on the airplane, everything goes in the inlet of the engine. The rain, the snow, the ice. That brings up the necessity for our anti-ice system, number 8 on our list. You see, with atmospheric conditions just right, ice can form on the inlet vanes, nose cone, and even on the first stage of the compressor. A buildup of ice could distort airflow to the point that compressor stall is inevitable. It's easily prevented, however, with an anti-icing system. The system ingredients are simple. We have a plentiful supply of hot, high-pressure air at the compressor exit in the diffuser case. And the nose cone and inlet guide vanes are hollow. Does that make the lights flash and the bells ring? Add a few feet of tubing and a control valve and one more essential part. An ice detection probe in the aircraft inlet senses the first formation of ice and opens the control valve. Hot air from the diffuser flows through the valve to the inlet section where it passes through and warms up the nose cone and inlet guide vanes. From there, it flows into the main stream of compressor air. Now, ice can't form on these heated parts of the inlet. When icing conditions cease to exist, the detector probe closes the control valve, and our icing problem is solved. They've just finished making some of their preliminary checks on the stand, so let's watch while they put the engine through its paces. The engine is at idle. That's about 60% RPM. Now the stand operator accelerates the engine on up to intermediate. That's full power from the gas generator with the augmenter off. That puts it at about 13,000 RPM and over 14,000 pounds of thrust. Of course, that's uncorrected data, and the engine is trimming itself. Trimming is the fine-tuning adjustments automatically made by the engine. Now he's taking it up to maximum. That's max AB. Did you see how that nozzle responds as the power setting is changed? What a beautiful sound that makes. That's full power from the gas generator plus everything the augmenter can put out. The thrust gauge is reading a little under 23,950. Now, back to idle, where trimming adjustments occur if required. That brings up another term you'll hear, cycle. We just observed one type of cycle, idle to max and back to idle. Another type might be intermediate to max and back to intermediate again. You see, we judge the durability of our engines and their components not only in terms of how many hours they will operate, but also in terms of how many cycles they will endure. When military pilots start putting their fighter aircraft through the hoops, these cycles really begin to add up, and this affects the lifespan of the engine. Looks like they're shutting down, so let's talk for a while about engine performance. Not the nitty-gritty numbers the test engineers deal with, but a broader picture. 4 yardsticks by which our engines are measured. Sure, there are many more, but these are the ones you often read about and hear about. First of all, engine thrust. What is the maximum thrust the engine will produce under certain specific conditions? We've pretty well covered that, but I haven't spoken of how big our engines are or how small. One of the smaller jet engines we have is made by our Canadian cousins at PW of Canada. It's the JT-15, rated at a max of about 2,200 pounds of thrust. Ever fly on a Boeing 767? That's powered by 2 of our PW4000s, rated right close to 60,000 pounds of thrust for takeoff. Then there's the thrust-to-weight ratio. How much thrust does it produce compared to its weight? It doesn't do much for our image if we build a fine engine, but it weighs 16 tons. If I build an engine that puts out 15,000 pounds of thrust and it weighs 3,000 pounds, that's a ratio of 5 to 1. Let's try harder and build one that develops 16,000 pounds of thrust and weighs only 2,000 pounds. 8 to 1. That's much better. Now we're becoming more competitive. And it's a continual battle to make that ratio better and better. How about fuel economy? With that limousine of yours, you might say, I get 24 miles to the gallon. The higher the number, the better the mileage. Not so with a jet engine. We speak in terms of TSFC, thrust-specific fuel consumption. And that turns out to be pounds of fuel used per hour divided by pounds of thrust produced. Our example shows a TSFC of 0.8. And if you'll look at the arithmetic, you'll see that the lower the number, the better. Your engine having a TSFC of 0.4 is better than mine, which has a TSFC of 0.6. These examples, by the way, are typical of some of our commercial engines. Military engines, because of their missions, run a little higher. And when the augmenter is turned on, the fuel consumption doubles or even triples. The fourth one, time between overhaul, or TBO. This one's simple. How many hours can you operate the engine before you have to remove it from service and totally overhaul it? Our commercial engines go 10, 15, and some 20,000 hours before overhaul. With a commercial jetliner flying at 500 miles an hour, in 20,000 hours it will fly 10 million miles. Why, that's, let's see, 400 laps around the world. Now, the TBO for fighter aircraft engines, much, much lower. That's expected because of the mission they fly. Sound the alarm, slap on your helmet, push the go lever, climb and straight up if need be, chase the enemy or be chased. On top of that, they're designed to put out the last inch of performance when they're called on. It's like comparing the Indy 500 with a drive to the church picnic. That's the way it is with engines for fighter aircraft. But whatever the TBO is, our people don't stop there. They refine and improve, boost that TBO again and again. In fact, they continue to do it for the life of the engine.